This lecture is going to be now on how to calculate entropy of reactions. On Canvas, I've supplied a table of thermodynamical values. I do apologize, it's really blurry. But when you look up the table, you're going to be given the formula. Next to that is going to be the enthalpy of the reaction at standard states. The next is going to be the entropy, I shouldn't say reaction, the enthalpy and entropy values of that material at standard states, and also the Gibbs free energy value of them. The units for all of these, as I also put down in Canvas, for delta H and delta G, they're the same. They are kilojoules per mole. But for entropy, they're kilojoules per mole Kelvin. We'll see why next time when we talk about free energy, delta G, as to why that is. So entropy has got the additional units of per Kelvin along with kilojoules per mole. Now, one thing about this is pretty rare. Actually, on the national exam, what they typically would do would give you a table of delta H values, which will be in kilojoules per mole. But then usually the delta S values will not be in kilojoules per mole. It'll be in joules per mole. And again, we'll talk more about this when we get into the Gibbs free energy equation. But be careful. If we have joules in one and kilojoules in the other, we do have to make sure they're in the same units whenever we do plug them into the delta G equation. But that's for another later time. The table that I've supplied for you, they're all in kilojoules per mole. All right. Okay, so to calculate entropy of a reaction, we are going to use the same exact equation as we did back in Unit 2. Instead of being enthalpy of formation values, we're going to be using entropy values of that material. And again, these are the values at 25 degrees Celsius. The first thing you do for these first three problems here is to write the balanced equation, including states of matter. States of matter are very important in order for us to determine the reaction, the entropy of the reaction, along with enthalpy, because states are so important with thermodynamics. I'm going to do problem 2, the combustion of hydrogen gas to liquid water. Okay, so hydrogen gas, H2, diatomic. If it's combustion, it's going to react with oxygen, O2, diatomic, producing liquid water in this case. Now we have to balance the equation, and to do so, we'll provide coefficients of 2 and 2 for water and hydrogen gas. Now when we use this equation for delta S up above, we always make sure we have to do the products first, the reactants second. It is state dependent, so when you look at your table of values on the tables that I've supplied you, make sure you're looking at liquid water and not gaseous water. So looking up the entropy value, which would be the second column after the formula compound, the entropy value for liquid water, okay, is 0.0699 kilojoules per mole Kelvin. We do have to account for the fact that there is a coefficient of 2 out in front of it. That's a step that most people forget to do. So we have to multiply this value by 2, and that would give us then the entire entropy of the products. We'll subtract from that the entropy of the reactants. Again, we'll take 2 times the hydrogen value. Now, these values are not 0. For enthalpy, it would be 0, but not for entropy. As stated before, to have a 0 entropy value, you must have a crystalline solid that is at 0K. Since all these reactions at standard state are 25, everything that you have will have an entropy value associated with. If this was a delta H reaction, both the hydrogen and the oxygen gases would have 0 values. So we'll take 2 times the hydrogen value, which is 0.1306. We'll multiply that by 2, and we'll have to add to that the value of oxygen, which is 0.2050. If I've made mistakes on any of you that have gone through these problems, let me know on Canvas, and I'll make sure to correct that. But I hope these are the correct values. Adding that up and then subtracting, we get an entropy of reaction that ends up being negative 0.3264 kilojoules per mole Kelvin. And that's how we calculate an entropy of a reaction if we are given a table of entropy values of each of the substances. Pretty simple. Just make sure that you do products first, reactants second, and then you make sure to multiply by any coefficients. Now we just got done doing equilibrium where we would square the value. Again, we got to be able to go back and forth with thermodynamics. If there's a coefficient, we multiply. If it's equilibrium, then we take it to that power. Go ahead and try problems 1 and 3 and see what you get. I'm not going to show it all out in detail. I did the values already, so go ahead and check and see what you get. For the first one up here, I get 0.1605 kilojoules per mole Kelvin. And for number 3, the entropy of the reaction I got was 0.1415 kilojoules per mole Kelvin. And for this one, it is reduced by hydrogen, again gas, iron, metal, Fe solid, and then gaseous water for this one. Okay, and see if you come up with those values. Now, one thing we have also talked about, along with calculating, more likely in a national exam, they will ask you to predict the sign. If we look at the top one here, number 1, the decomposition of calcium carbonate, we would have a solid calcium carbonate decompose into solid calcium oxide and gaseous carbon dioxide. Because we are producing a gas, we would predict or should predict that the entropy of the reaction is increasing or has a positive value because the gaseous state has got so much entropy associated with compared to solids. Therefore, on the national exam, if they asked justify the sign on the entropy and why, you would say the entropy value would have a positive value or greater than 0 because the gaseous state of the product carbon dioxide has much more entropy, more disorder than the solid state calcium carbonate that it starts with. Therefore, the predicted value would have a positive value. We see when we calculate the actual value, we do indeed have a positive value, which corresponds to the prediction. One other note about this, if any of you try the bottom one with calcium hydroxide, the dissolution of calcium hydroxide into water, oops, my mistake. That should be calcium ions and 2 hydroxide ions. This is solid state. If you were asked to predict the sign in this, again, we would predict the sign of this reaction to be greater than 0 or have a positive value because the disorder or the order of ions, it's less order than a solid state. So again, we are going to a more disordered set of products, and therefore we would expect the entropy, the chaos, but use the word entropy, would be increasing because aqueous ions have got more disorder than solid state materials do. Now, I did this problem mathematically, and however, when I do it, or you do it, the delta S value of this, if you use the values on the table that I gave you, ends up being a negative value. Now, you might ask, why does it not match the predicted sign? And that's because this is involving multiple other variables. We're not including the actual water itself, and therefore there's other variables to look at. So if any of you did that and saw the disparity, I just wanted to make a note about it. On the national exam, however, you would predict a positive value. Almost all substances, when they dissolve in water and dissociate ions, we have an increase in entropy because ions have a higher degree of entropy than solid state materials. On the very bottom here, again, we're looking at predicting the sign of these. And you can read there what it says, predicting ice melting. If we looked at the entropy of value of this sodium associated with this, a state change, we're going from solid to liquid. Now, the entropy of this reaction we would predict to have a value of positive, greater than 0. Why? Because we're going to a liquid state which has less order than the solid state. So we're going to a product, okay, or doing a phase change in which the substance has got less order in the product state than solid state, and therefore there's an increase in entropy because of the less order created in the liquid state compared to the solid state. And then you go about. Now, does this happen naturally or spontaneously? That has to factor in other situations. It has to factor mainly with temperature. Because we do the enthalpy of the reaction, okay, we know that when we melt things, that it is an endothermic process. When we have an endothermic process, this is not thermodynamically favorable, but this one is. And that'll be the next lecture, is when we have one that is, entropy is favored, but enthalpy is not favored, how do we know if this reaction will be spontaneous or thermodynamically favorable? Will this reaction actually occur? And the key to that is the temperature. If the temperature of the surroundings is over the melting point of water or ice, if the temperature is greater than 0 degrees Celsius, the surroundings is warmer than the melting point of the material. Therefore, energy is going to flow into the solid, causing it to melt spontaneously. So this is where we have to take into account the conditions, in this case temperature. And when we do, we can figure out if this process is thermodynamically favorable or not. And that's what the next lecture will deal with when we start talking about delta G, or Gibbs free energy. Okay, mathematically very simple equations. Conceptually, that's what you should really focus in on. Look at reactions, look at the signs on the products and reactants, look at their states. And again, always realize solid has got the most order, then liquids, then aqueous ions, and then gases. If we're going in this direction from left to right, we're increasing the entropy of the material and having less and less order in that state of matter. So it's a states of matter question. Look at it and use the states of matter to justify your equations, which is the first homework I have in this set, is asking you to look and just justify the sign of the reactions. You should now be able to justify at least the delta S and delta H values on those. And then tomorrow I'll talk about how we can then use Gibbs free energy to predict the sign of delta G. Thanks again for listening.